Every generation, a breakthrough changes the course of humanity. The engine unleashed speed. The train unlocked travel. And the splitting of the atom released atomic power. Now, engineers are taking these inventions to the next level. Will a revolutionary engine drive the world's fastest motorcycle?
This level of what's possible was unimaginable just a decade ago.
Can a train break the speed of sound? And will an energy source hotter than the sun power the world?
ITER is the largest science experiment that's ever been built. It's unprecedented.
These are the biggest breakthroughs. Now, on Project Impossible. Imagine the fastest production bike ever created. 250 horsepower. 0 to 60 in 2 seconds. And a top speed of more than 200 miles per hour. This isn't the creation from a motorcycle powerhouse, but the goal of a small startup operating out of a shop in San Francisco. Lightning Motorcycles.
Technology moves forward most rapid in periods of war and in competition. And competition is preferable to war.
To take down the competition, their superbike will need the most powerful engine on the planet. A nearly impossible challenge. The best engines in the world only convert 20% of fuel into energy. The other 80% comes out the tailpipe.
Combustion technology is well over 100 years old now, and there's been a huge amount of progress, but still the overall efficiency is not very high. If you think about pistons going up and down to make a crankshaft revolve and explosions, you're just wasting energy. How do we make something better?
The team abandons the motor with thousands of parts and tries out an engine that has just one. The electric motor.
The basic functions of induction motors has not changed a lot since Nikola Tesla time. And that motor was magnetism and electricity.
An electric motor is the model of efficiency. 90% of the power that goes into the engine comes out as torque.
We've got a motor that makes over 250 horsepower, more than double the torque from a MotoGP bike or a world superbike.
But unlimited torque creates unexpected problems. In bench tests, the motor bent bolts and snapped chains. The question becomes, is it safe to engineer a bike with this much power?
If you're accelerating down a straightaway at 150 miles an hour and you pull a bolt, it's serious business.
For a startup, designing a motorcycle from the ground up is an expensive proposition.
The old way of doing it was coming up with a design, drawing it up, going to a casting house, make it, try it. You know, you can be hundreds of thousands of dollars into making a part before you ever find out whether that part works.
To level the playing field, they use a variety of new technologies, including a powerful piece of software called Inventor. With Inventor, the team can stress test a part while it's still in the computer. Then, when they are ready to build a prototype, they skip the casting house and fire up this machine. A computer numeric cutter, or CNC. Using a drill bit and a pre-programmed sequence, a CNC can transform a block of raw aluminum into any part they want in less than an hour.
This whole process now has opened up manufacturing where a small company can build a product that rivals the largest companies in the world.
Using this state-of-the-art equipment allows the team to build the bike the old-fashioned way.
All the bikes are assembled by hand, by people. Everybody that works here takes great pride in their work. They all have a huge part to play in where we're going.
But all this work will go to waste if the bike is too heavy. To keep the bike's weight down, its shell, or fairing, is made entirely out of carbon fiber. This fabric is lighter than aluminum and stronger than steel.
John, our carbon fiber specialist, has been working around the clock to develop a complete new set of bodywork that is structurally sound, physically light, and beautiful in appearance. So when you see the bike and you see the carbon fiber bodywork, that is the LS218.
The final bike comes in at the same weight as a gas bike. But can it go faster? Thunder Hills Speedway. 2 miles of twists and turns. This is the perfect place to test the new Lightning against a gas superbike. A tough challenge. This gas superbike has 160 horsepower and can go from 0 to 60 in 2.9 seconds. But it has a weak spot.
In a combustion bike, you need the ability to have several gears to be able to use the power of the engine effectively. Every time gears intersect, you lose as much as 7 or 8% of the energy.
The Lightning's electric motor doesn't need a gearbox. When the rider opens the throttle, the electric motor goes from first to fifth gear instantly.
Electricity moves at the speed of light. Something magical about twisting a throttle and having this huge hand just shove you down the road.
Is this power too much for a professional rider to handle?
My name is Jim Hoogerhide. I'm a union electrician, and I spend all my free time and money racing motorcycles and cars. First time I got on the Lightning, I was a little concerned about 248 rear-wheel horsepower on a wet track. But the feel was incredible. It's so instant and immediate. You're not slipping the clutch, waiting for the power to come on. It just pulls, pulls, pulls like a freight train.
When the bikes dive into the corners, the differences are even more pronounced. The gas engine's pistons, moving at thousands of RPMs, create gyroscopic forces that force the rider to fight the bike into the turf. The Lightning's electric drive has no gyroscopic forces because there are no pistons.
It just flips side to side so much easier. Controlling rear wheel slide and front end push and things like that. Road racing this thing, so much easier.
All these advancements help the Lightning dominate on the track.
Every time we brought the bikes to the track, we consistently podium finished 1-2.
Still, there's one title that can only be won on the salt flats of Bonneville.
where else can we hammer down for 5 miles?
Other teams are on the verge of similar breakthroughs. A supersonic train and a power source hotter than the sun. On Project Impossible. Welcome to a place so inhospitable, almost nothing can live here. So flat, you can see the curvature of the Earth. And so wide open, racers call it the fastest place in the world. Utah's legendary salt flats, Bonneville.
We come out to Bonneville because where else can we hammer down for 5 miles?
Bonneville Speed Week is the mecca of land speed racing. Teams bring anything and everything with one goal: add their names to the record books.
The history of land speed racing is deep and rich. I love that this is really the last unsponsored race. There's no real glory in this except amongst us.
For over a century, Bonneville has been the place where pioneers have pushed the limits of what the engine can do. A fact seared into history in 1935, when Malcolm Campbell set the land speed record at 300 miles per hour, fast enough to melt the tires. Most of these cars were built in the family garage, even the ones that could go 700 miles per hour. Now, the Lightning crew has come to Bonneville to prove that the future of the engine is electric.
When I first started racing the Lightning, everyone thought, oh, that's so cute. You're going to go down the course, but you're only going to get so far before the extension cord yanks out. Then, we came out, we went, I think, 189, and their jaws hit the floor.
This is a weird animal compared to our checklist.
Yes. Scratch. We're going to get a new one.
Yeah. In 2011, the Lightning set the record as the world's fastest production motorcycle, hitting 216 miles per hour. But can it go faster?
I think that's nowhere near the potential that this bike has. I'm sure it's capable of going 250 miles an hour plus.
Easier said than done. The conditions that make Bonneville ideal for racing also make it dangerous.
Salt's she's a harsh, salty mistress. A lot of it is just managing traction.
Driving on salt is like riding on snow with a slick tire.
At speed, it really just kind of floats about the salt.
To help gain traction, they lower the tire pressure. And there's another hurdle. At 200 miles per hour, the bike will face air resistance stronger than a Category 5 Hurricane. To reduce this effect, they outfit the bike with an aerodynamic nose and tail fairing. This creates a pocket that protects the rider from being blown off the bike. But that's all they can do. The rest is up to the rider.
See you later.
After a minute and a half, it reaches 200 miles per hour. Not fast enough to increase its record.
The bad news is we only ran 200 miles an hour.
Yes.
The good news, you were under half throttle most of the time.
Yeah.
Jim couldn't go faster because slick conditions caused the rear wheel to spin out.
Here at 188, your rear wheel is going over 20 miles an hour more than the bike is going. Look at the wheel span.
I know.
Bum, bum, bum,
It's
bum,
just-
bum, bum.
We're not going to do much with that course.
Still, 200 miles per hour on half throttle is fast enough for one important man to take notice.
Today I got to meet Mr. Honda. Not like, you know, some dude named Honda, Mr. Honda. When we have the head of Honda wandering up to us on the start line at Bonneville and introducing himself and handing out his business card with his personal cell phone number, there's a shift.
The reason? The bike that can go 200 miles per hour in Bonneville is the exact same bike that can go from New York to Boston on a single charge.
My whole life, it's just been accepted fact that if you want more power, you're going to pay a big penalty. With the electrics, a more powerful motor is more efficient than a less powerful motor.
As the world transitions to the electric motor, there are those who worry that the era of speed is over. But the Lightning proves we are only at the beginning.
This is much bigger than setting speed records and winning races. This is the opportunity to help the world transition to a sustainable form of transportation without having to give up everything that we enjoy.
500 miles away, teams are working on another breakthrough. A train that can break the speed of sound. Next, on Project Impossible. For more than 2 centuries, trains have been a symbol of progress. The first train, Stephenson's rocket, traveled 28 miles per hour. Today, bullet trains can reach 250 miles per hour. Now, a new type of train promises to go even faster. It's called the hyperloop.
Imagine a train inside a tube moving at very high speed.
Current trains are limited by air resistance. The faster they go, the more air pushes against them. Placing a train inside a vacuum removes this barrier.
And with that, you can reach speeds that are even higher than what commercial airplanes are doing nowadays.
Nobody has ever attempted this idea before, which is why one man is holding an international competition to see if it's possible. The founder of SpaceX and Tesla, Elon Musk.
What this is really intended to do is to encourage innovation in transport technology. And I think we'll find that it's way more incredible than we ever realized.
They said to the world, you guys create a team, come up with design, and we're gonna select the best design that we're going to race down a track that we're building ourselves in Southern California.
30 teams from around the world will need to push the limits of existing technology to pull it off. In Allentown, Pennsylvania, a team of undergraduates at Lehigh University believe they have the right stuff.
The big thing for us is we wanted something that was real, something that if we decided to go out and professionally build tomorrow at a full scale, it would run.
Like all teams, they must solve the central problem of the hyperloop. They need to find a way to levitate their pod. Because at 700 miles per hour, the friction will burn up any tire.
There's only so much speed you can get out of those before they break. And the idea was that by using air pressure, we'd be able to levitate our pods, that way we get rid of that friction.
But this isn't as easy as it sounds. Moving a 300-pound pod down a track demands more air than the tanks can hold. To solve this problem, they use every last particle of air they can find.
Unless it's a total vacuum, there are some air particles that build up over time. So we use a turbine fan in the front to suck air in and feed it into a compressor area.
This brings in enough air to keep the pod aloft for its entire run down the track.
Everybody else can maybe get enough to float for like 20 seconds. With our compressor, I will be able to go 15 minutes, 30 minutes, 45 minutes on a full load.
As Lehigh's hyperloop pod is coming together, so is the entry of a rival team. Our Loop is the only non-student team to make the cut. Its 140 members from 14 nations collaborate via the web.
What's up, Dennis?
Hey, what's up?
Someone posted on the message board Reddit a message saying, hey, let's create a group to tackle the SpaceX Hyperloop Challenge. Everybody was driven by the idea of let's make something together. And voila, our loop was created.
Our Loop's method of levitation is as unorthodox as their team. It uses a revolutionary technology: magnetic levitation. It makes the dream of Marty McFly's futuristic hoverboard a reality.
It's a bunch of magnets that you put on a motor, you make them spin very fast, and when you put that over a conductive surface, you have the whole thing levitating. So we have 8 of those ArcSparks engines that are providing the levitation of our pod.
Each hover engine can lift 130 pounds.
They have huge power requirements just because they have to spin up really fast. All 8 hover engines require about 400 amps of current.
That's enough to power 4 homes with every appliance turned on. This means the team must build custom batteries.
These are highly unstable batteries. The reason why it's so dangerous is because it's very energy-dense cells.
Once assembled, every finished cell is tested in a blast chamber.
I started the charge now.
It is a very high possibility that these batteries can overheat and catch fire.
For most teams, building batteries would be too risky.
Here we go, here we go. All right, we've activated the protection circuit.
But for our Loop, their unique structure allows them to pull it off.
I worked at Tesla Motors for 6.5, 7 years. Retired from there a couple months ago. Got bored sitting at home, and I just started putting my knowledge that I had working with batteries at Tesla to work for the R Loop team.
And
Yes.
there it is. All right.
Hooray!
Our Loop isn't the only team taking risks to build the train of the future. Other teams believe they have what it takes to claim the top prize in the Hyperloop competition.
Nothing's impossible. If you put your mind to it, you can dream it, you can build it.
The big showdown coming up next. Around the world, 30 teams are vying to win Elon Musk's Hyperloop competition. Each is building a prototype for a supersonic vacuum tube train that would zip passengers between San Francisco and LA in half an hour. A tough challenge for the best engineering programs in the world, let alone a high school team. St. John's is the only high school to advance this far, beating out nearly 1,200 entrants to do it.
It's been a challenge to balance college applications and testing with the Hyperloop, but I found a way to make it work.
They built a fully functioning pod that uses air pressure to float above the track.
It's still kind of like shocking to me how much we've accomplished, how far we've gotten, and it's starting to come together, which is awesome.
To keep their pod from becoming a missile, they are adapting a braking system that is normally used to stop roller coasters.
We're using eddy current magnetic brakes in order to slow our pod down from 200 miles an hour. So as these magnetic tracks go along the surface of the aluminum track, they will slow our pod down by inducing a magnetic field onto the aluminum I-beam.
What Team Hyperlift lacks in numbers and funding, they make up for with resourcefulness.
Our team decided, because of the limited size, to actually work with as much off-the-shelf material as possible.
That approach could prove invaluable as they try to solve one of the Hyperloop's unique challenges. Since the train will be inside a steel tube, using traditional methods to track it, like GPS, won't work. The St. John's students find the answer at the local mall. Radio frequency ID tags. They are used to track retail merchandise.
It's a tiny little chip that has maybe 100 different characters on it. What happens is when the signal touches that tag, you energize that tag and get the data back from it. How we're applying that to the track is each different checkpoint, let's say 100 meters in, 200, 300, is going to be a different code.
Will these innovations be enough to unlock a new form of travel?
If we can get one piece of technology out of our pod that moves on to full scale, that's an accomplishment.
On the day of the competition, the teams are eager to prove their engineering will make the cut.
How's everybody doing? So this is what the future looks like. And it is rare in our lives we get to feel that moment. And today, we're looking at the very first Hyperloop pods ever.
It's really cool to see all the different designs. There is a lot of variety of approaches, and it's just great to see that energy. Everybody just wants to make the Hyperloop happen.
The technology faces enormous hurdles. Every pod must endure a battery of safety checks before it is allowed to run. Out of 30 teams, just 3 make it to the final run. Lehigh's Hyperloop isn't one of them.
The only disappointment could be not getting to the big 2. But honestly, just getting to this point and turning it on and watching it work with nothing break, that was a great experience.
Our Loop and the Texas teenagers are also out of the running. But coming this far is an accomplishment.
Everyone here is so knowledgeable and so passionate about the Hyperloop. Oh, so sorry. Elon Musk is here.
Yeah, I heard you guys did real well.
Thank you so much.
Thank you.
You're re-entering the second competition too, right?
Potentially, yes.
Potentially.
Well, some of us are graduating, so.
Why does that matter?
It doesn't matter. We're entering the competition. Absolutely. 100%.
The hopes of a new form of transportation are now riding on 3 teams. Will any one be enough to make Hyperloop a reality? The first team reaches only 66 miles per hour. The second pod malfunctions.
Enabling manual overrides?
The entire competition comes down to the third and final pod. The pod passes 200 miles an hour, opening the door to a new era of travel.
I think this is really the first milestone in the future of transportation, for sure.
Halfway across the globe, engineers are working on an even bigger breakthrough, as big as the splitting of the atom. In the world of energy, every leap forward has come with a cost. Oil powered the industrial age, yet created pollution. Nuclear fission unlocked the power of the atom, but created toxic waste and meltdowns. Now, a global team is on the verge of unlocking the Holy Grail.
We're trying to find a future source of energy which the human race can rely on for thousands of years, which doesn't contribute in any way to climate change, and which is also inherently safe and which everyone has access to.
The answer: nuclear fusion. The process takes the most common element in the universe, hydrogen, and fuses it into one of the most stable elements in the world, helium.
Fusion doesn't produce any carbon dioxide, any carbon monoxide, any highly radioactive waste. It produces helium. You can blow up your kids' balloons. Okay, that's the end product of the reaction.
A single pound of hydrogen could light up every home in the U.S. But the only place in the solar system hot enough to create fusion is the sun. Until now. Hidden among the fields in the south of France is the boldest experiment in history. Inside this nondescript building, scientists are creating the International Thermonuclear Experimental Reactor, or ITER.
ITER is the largest science experiment that's ever been built. It's a collaboration of a total of 35 nations. It's unprecedented.
The project is so ambitious, it will take the combined effort of every industrialized country in the world, from the US to Russia to India.
We have to work as a team. If not, no chance to succeed.
The core of ITER will be a reactor called a tokamak. The reaction will start inside this donut-shaped vessel.
The first component that's important is the vacuum vessel. We pull all the air out and then put in a little bit of the hydrogen to start the fusion reaction.
As the hydrogen spins, heat turns it into plasma. The plasma becomes so hot, it fuses to form helium and huge amounts of energy. But in order for the tokamak to work, temperatures inside must reach 150 million degrees Celsius. Not just as hot as the sun, 10 times hotter.
It's unbelievably hot. If this plasma touched any of the components, it would melt them.
No material can contain the plasma, not even pure diamond.
How do you hang on to a fuel which is at 150 million degrees without melting the material structures around the fuel? Well, we do that by using very strong magnetic fields.
As the hydrogen fuel moves through the tokamak, a superconducting magnet suspends the atoms in midair. This way, they never touch the reactor's walls. But in order to work, they must build the largest magnet on the planet. In San Diego, California, General Atomics is taking on the impossible. ITER's magnet will be 6 massive coils packed with enough superconducting cable to reach the sun and back 5 times.
No single country had the capacity to produce it. Matter of fact, the world didn't have the capacity to produce it. 6 of the members have increased their production considerably.
For each coil, several individual sections of cable must be joined together.
It's a very critical process. We don't want to get the cable inside too hot, and we don't want to burn into that cable because then we damage the coil. So we use a series of automated welding machines to do that work.
When joined together, the huge coil weighs as much as a locomotive and can be moved only by this heavy-duty hovercraft.
If you take an air hockey table and turn it upside down, that's really what our transport tool is. So what we have is big air bearings that are blowing air down onto the floor and elevating the whole coil up. So this air now is lifting this 250,000-pound coil up off the ground, and we're hovering on a cushion of air.
The coil's destination is a specially built convection oven, where it must bake at 1,200 degrees Fahrenheit for 5 weeks. This intense heat morphs the materials into a superconducting magnet called a solenoid.
The magnetic field coils on this machine, they're very large, so much bigger than sort of a magnet that anyone would be familiar with.
Strong enough to pick up an aircraft carrier. To create this force, the solenoid draws 47,000 amps of electricity. This generates enough heat to fry the magnet's cables. Inside this building is ITER's answer. A 3 million pound stainless steel deep freezer called the cryostat. The idea is to encase the tokamak and keep it at an incredible -452 degrees Fahrenheit.
The temperature inside the cryostat is very important because those superconducting coils are maintained at very low temperatures, so just 4 degrees above absolute zero.
This is colder than the temperatures on Pluto. And just meters away, the plasma will be the hottest thing in the entire solar system. Which leads some to wonder, is fusion really as safe as scientists say it is? Or is it the next Chernobyl? Find out on Project Impossible. Few breakthroughs in history have changed the world as much as the Manhattan Project, a top-secret World War II program to build the atomic bomb. Scientists split the atom in a process called fission, releasing huge amounts of energy. But there is a far greater source of atomic power that exists: nuclear fusion.
In fusion, we're taking hydrogen and putting it together to form helium and a lot of power.
Now, 35 nations have joined forces in the next big experiment. They are building the world's largest fusion reactor.
What we're talking about here is an energy source which is clean and abundant and safe. And what we're trying to do is to determine if it's possible and how it might be done.
The conditions for fusion are so sensitive. They have to build a one-of-a-kind structure to protect the reactor from every disturbance, like an earthquake. They select the perfect place to house the tokamak, a limestone quarry in the south of France. Workers begin by digging a seismic isolation pit in solid limestone.
The volume of rock excavated represents the same volume than the Great Pyramid of Cheops.
Once the bottom is perfectly level, they install 493 shock absorbers, called isolation pads, to support the complex.
This device is mainly to filter the acceleration of a ground in case of earthquake. And actually, the building will be able to move by roughly 10 to 12 centimeters.
These pads shoulder the reactor, protecting it from the outside world. But what sits on top of them protects the outside world from the reactor. With a tokamak, scientists aren't concerned about a meltdown. Fusion is as safe as boiling water.
If you have a problem, the energy will be lost and it won't get hot enough to sustain itself.
It's the superconducting magnet that's the problem. If it overheats, it can explode like a 20-ton bomb. To protect the workers from the worst-case scenario, ITER is building a 10-foot thick protective ring called the BioShield.
The BioShield is the last line of defense. It's the main way that we isolate the tokamak from the rest of the world.
To contain the potential blast, crews lay down a web of steel 5 feet deep. Next, they pour a special mix of concrete that contains 60% iron ore, which can block and absorb radiation. Any air pockets will weaken the BioShield, causing it to fail. These are usually prevented by agitating the concrete. But the BioShield is so dense with steel rebar, agitators won't work. The solution, a special concrete that compacts itself into one of the strongest barriers on the planet.
The tokamak himself is 23,000 tons, is 3.5 times the weight of the Eiffel Tower.
Construction of the ITER complex will continue right through 2021. And in 2025, the world will have a working fusion reactor.
The fuel is nearly unlimited. There is many hydrogen atoms worldwide, and there is enough fuel for maybe 100 million of years.
ITER not only can power the world, but might also bring us together.
It's something that not only is scientifically and technologically interesting, it's also culturally interesting and could in fact be a model for how can the countries of the world work together to solve a global problem.
When engineers put their minds to it, no challenge is impossible.